Okay, first I'd like to start off by thanking the organizers for this really nice conference. Today I want to talk about a work that was done in collaboration with Gal Shavit, who's a postdoc at Caltech, and Liang Fu, who's here in the audience, and it's called Engineering Higher Hall Crystals. Here is an outline of my talk. First, I'll start with an overview of topological quantum crystals. Then I'll try to bring us to the modern day and discuss quantum crystals in connection with some recent experiments. And then I'll move on to our work, which is on realizing a practical setup, which comes with an analytically controlled and pretty simple theory of possibly higher Chern number Hall crystals using pretty simple ideas from Moiré engineering. This is a work that recently appeared on the archive. So I want to start a bit more broadly with quantum crystals. Quantum crystals are quantum phases of matter where the translation symmetry is spontaneously broken by interactions to some lattice. And in 2 dimensions, we can classify them into 2 broad classes, one which I'm calling trivial and one topological. And the trivial quantum crystals, also known as Wigner crystals, are by far the more well-studied, and they were first theorized in 1934, and they have a rich history, and they were recently observed in some really interesting experiments, just flashing some data here, some STM data. And their distinguishing feature is that they have Chern number 0, and topological quantum crystals are simply those that have Chern number, which is non-zero. And 2 examples are theoretically proposed Hall crystals, which were proposed around 1989, and then more recently anomalous Hall crystals, which are distinguished by not requiring a magnetic field. And I'll discuss these more, and these will be the topic of the current talk. So just to give some more, a few more facts comparing and contrasting trivial and topological quantum crystals. Trivial quantum crystals have 1 electron per unit cell. The unit cell is defined by the density of electrons because translation symmetry is spontaneously broken by interactions. Whereas topological quantum crystals can have a continuously varying number of electrons per unit cell, which is sort of weird. It confounds our intuition about insulators. But it's possible, and certainly theoretically. For trivial quantum crystals, there exists a classical point particle limit. In some regimes, they can just be understood as point particles repelling by Coulomb. Whereas for topological quantum crystals, there is typically no classical point particle limit. And this is a result of the fact that there's a topological obstruction to thinking of them in terms of exponentially localized Wannier orbitals. That's what I'm alluding to here with the graphic. And as a non-essential fact, I just wanted to add, typically we expect the lattice for a Wigner crystal to be triangular in 2 dimensions, whereas it's still, I'd say, an open question what it is for topological quantum crystals. There's some theoretical work showing that it's honeycomb, which is sort of consistent with our intuition that you require multiple sublattices for topology. But that's an interesting question, I think, still actively being researched. I want to attempt to bring us up to date and just situate this work in the field a little bit more by talking about the modern status. Hall crystals were initially studied because people thought that the Wigner crystal and the fractional quantum Hall state in the lowest Landau level, rather than compete, maybe they could coexist in the form of a Hall crystal. But since their first proposal, it's no longer believed to be realized in the lowest Landau level. And indeed, there are actually few realistic theory proposals. That sort of changed with the entrance of Moiré materials, which allows for a broad range of tunable platforms, which can realize all sorts of phases of matter. And in particular, in the last few years, anomalous Hall crystals have garnered particular attention. These are Hall crystals which exist at 0 field, and they've possibly been observed and certainly theoretically explored in a class of Moiré materials. Just a non-exhaustive list here on the experiment and theory side. So it includes twisted bilayer trilayer graphene, rhombohedral n-layer graphene, the latter from the group of Longju at MIT. And here I'm just presenting a figure from a recent paper by Longju's group on 4-layer rhombohedral graphene, showing what I believe could be a typical signature of Hall crystals or anomalous Hall crystals. Here, just to orient you, this is filling on the x-axis and let's see, displacement field on the y-axis, and the color is RXY. And you see a broad region where RXY is approximately constant, and the region extends over order 1 filling, and that's something that you wouldn't expect from disorder broadening of a Hall plateau alone. So it's a possible signature of an anomalous Hall crystal. And on the theory side, there have been many groups, I'm listing a few here, that have worked on these topics in recent years, maybe the last 2 years. And I want to point out that most of these works involve Hartree-Fock and ED and are not analytical theories necessarily. Okay, so now I want to, yes. Yeah, the STM experiment was just a Wigner crystal, and so indeed I think the dominant evidence is just from transport, not from some real space charge density mapping. So this leads me to the current work, where we propose producing Hall crystals from a moire in a pretty simple theory. And the platform I'm proposing that I'm going to focus on here in this talk, I've illustrated it here. The basic idea is that there's an active layer, such as a 2D semiconductor or graphene, in an out-of-plane magnetic field, on top of a 1D modulation, which could be produced by some dielectric patterning, some substrate. And the essential physics is simply 1D modulated Landau levels. That's the theory that I'm going to be considering here. The basic idea that I want to convey is that you start with a metal, which consists of chiral edge modes of the quantum Hall strips that live in this Landau level that's been modulated. And with interactions, they break the remaining translation symmetry and produce a Hall crystal with diverse Chern numbers. I'll try to explain how this arises from a simple model. So the starting point, theoretically, is analyzing a 1D modulated Landau level. And so I want to establish that the theory is really just an array of quantum Hall strips, let's say along the y direction. And we choose a particular regime to study this analytically. This can be studied many different ways, but we choose a regime where we can really just treat the edge modes as being the active degrees of freedom. And the low energy physics therefore becomes a series of coupled chiral edge modes. And that's what I've tried to illustrate here and here. This is along the y direction, and these edge modes are chiral, so there's some down movers and some up movers, and I've labeled them with this operator psi. And this is an in-plane view where I've illustrated the modulation going up and down and the quantum Hall strips sort of filling the potential landscape. Okay, so now I just want to introduce the interacting instabilities of the model. It turns out that the interacting instabilities are of this form. I've illustrated it as a 4 fermion operator, and you can think of this as a correlated hopping. The wires are coupled as soon as you turn on interactions, and they couple in a certain way, which I've given 4 examples here, and I think the examples basically serve to illustrate the most general form. They're correlated hoppings in each direction, same distance along x. So this is a hopping between edge modes of the same strip, and this is a hopping between edge modes of neighboring strips. And you can have longer range hoppings, and the point is that natural realistic Coulomb interactions involves a sum over all sorts of different hoppings, and we have to analyze all of them if we want to treat this analytically properly. I just want to point out some scales. This is what I'm calling a moire length scale A0, and this is the width of the quantum Hall strip, which is proportional to the filling. So you should imagine these green regions as being tunable with filling and density. Okay, and just to rehash my claim, I would claim that the charge density, which is modulated only along the x direction without interactions, upon turning on interactions, becomes a charge density wave in the y direction as well, and at the same time acquires a Chern number. And this is a heuristic picture of before and after turning on interactions. This is a formula for the wave vector along y, which I probably won't have time to to explain in detail, but you can see that it relates the Chern number, the magnetic field, which is 1 over L squared, the moire period, and the filling. So they all occur in this formula, and it's continuously varying. The examples that I presented previously, I'll just label their Chern numbers here. So when the edge modes couple between within the same strip, you get a Chern number of 0. In this example, sort of like in the SSH model, there remains gapless edge modes, and it's a Chern number of 1. And these various other examples can lead to various other Chern numbers. And perhaps the surprising thing is it's not always going to be Chern number 0 or 1. There are non-trivial regions of phase space where you can realize diverse other Chern numbers. And I think I'll run through this slide really quickly. I just want to point out that there is an analytical derivation of the wave vector, which relates it to perhaps a fundamental equation of Hall crystals, you can call it, known as a Diophantine relation, which relates all the relevant quantities, the electron density, the flux density, the Chern number, another invariant called eta, the area of the unit cell. These are all continuously varying, but they satisfy a definite relation given here. And you can use this relation to back out the Chern number, the wave vector, and it's all pretty tightly constrained, but each phase has its own set of parameters. Okay, and now I'm finally presenting a microscopic phase diagram. This is simply Landau levels in a 1D modulation analyzed fully, considering all possible Coulomb interactions, studying the system to find the most relevant instability, and then declaring that to be the ground state. This is a perturbative RG approach. But on the x-axis, you see that the magnetic field, on the x-axis, you see the magnetic field, and on the y-axis, you see filling. And labeled in these colored regions is the Chern number of the given phase. And so the gist here is that higher Hall crystals can be stabilized. This doesn't depend strongly on the form of the interactions. Nothing's too finely tuned here. And real quick, I want to also explain that there's a simple way to understand all of these phases. Maybe too simple in retrospect. The phase diagram is approximately coming from simply minimizing the wave vector times the magnetic length minus an order 1 number. What that really means in physical terms is that the system wants to form a unit cell, wants to form a period along the y direction, which is always has wave vector approximately 1 over the magnetic length, up to some non-universal constant, which depends only on interactions. It might change depending on the Landau level index and so on. But as you can see here, that if you simply follow this protocol, you can pretty well reproduce this phase diagram, this protocol of minimizing a quantity for a single tunable parameter C star equals 1. I want to finally just real quick bring it back to experiments. The one thing that I find suggestive is that a lot of experiments do observe these wide regions in phase space, order 1 regions in filling of a constant or approximately constant topologically quantized response. And this is certainly consistent with a Hall crystal or some sort of theory involving Hall crystals, which sort of defeat the Strata formula, and they have a quantized response over a wide region, not just a narrow line in these sorts of plots. And I think it'd be interesting to further explore the connection to recent experiments. Okay, so with that, I think I'll just flash my concluding slide here, and I'm happy to take any questions. Oh, do you want this?
No, it's okay. Would you call, so let's say in Hartree-Fock theory, in a Landau level, the lowest energy states for filling factors smaller than a half are an electron Wigner crystal, and the lowest energy states for filling factors bigger than a half are a whole Wigner crystal with quantized Hall conductivity 1. So my question is the whole Wigner crystal in a Landau level a Hall crystal?
Yeah, so the question is the whole Wigner crystal in a Landau level a Hall crystal? Yeah, my answer would be yes. I think that's the standard understanding. But in some sense, I want to make a distinction between this and that, which is that that's in a sense more trivial because the topology is coming from an inert filled band that you dope on top of, whereas the topology is really coming from the crystal here. Without the crystal, there wouldn't be a quantized response of the same Chern number. Does that
Of the Chern numbers
of the Chern numbers that are presented.
differ from one.
Exactly. Chern numbers are different from 0 or 1. Yeah.
But in the experiments,
Uh-huh.
maybe this, maybe the experiments say that you have
Mhm.
the ground state in this regime is a Wigner crystal of holes in the Chern 1 band.
Yeah, indeed. The experiments seemed perfectly consistent with a ground state of a Wigner crystal of holes over an inert Chern band, and yeah, it'd be interesting to figure out the difference. I think there's some terminology that needs to be also discussed. Yeah, the Chern number certainly can change from like +2 to -2 in this phase diagram, and I think the best way I have of understanding this is sometimes if you simply take this as your protocol, sometimes you do want a Chern number. So C depends on the Chern number as follows, and this formula has a duality under nu goes to 1 minus nu, and Chern number goes to 1 minus Chern number, and that's a particle hole and inversion symmetry of the theory. So sometimes you do want a negative Chern number when you say take filling to 1 minus filling, or you want to flip the Chern number as well.